Okay, welcome back to chapter 17. This is a pretty exciting chapter. I really like inner product spaces. You can see that's the title of the chapter. They're one of the most useful techniques we have for solving linear differential equations. And it turns out most of the equations you run into in classical and even quantum physics are linear. One of the reasons is that the nonlinear ones are so hard, so they're hard to solve, so we try really hard to find linear ones instead. But we can find a lot of linear equations, and so those are the ones that show up a lot. And then inner product spaces in many ways are the ways that we have to solve those. And in particular, this word that's probably been tossed around that you may or may not have heard before, and it's the name. It's named after David Hilbert, but a lot of people will refer to these as Hilbert spaces instead. I should point out a caveat that Hilbert spaces are a specific kind of inner product space. They're an inner product space that's called complete. And complete has a very definite mathematical meaning. It basically says that no matter where I go in a space, if I'm walking in some direction and I eventually stop walking, that wherever I end up actually exists in that space. It's maybe the most colloquial way of thinking about it. But that's what you need to kind of generalize an inner product, or at least the opposite of generalize, make more specific an inner product space into a Hilbert space so that you can actually work with it in a lot of PDE's situations. But anyway, so this word Hilbert space is probably what you want to be thinking of, even though technically we're only going to be covering inner product spaces. If anybody ever refers to a Hilbert space, that's what they're referring to. So we're going to jump back into vectors. It's just starting out with vectors in R3, because we're going to try to generalize this idea of the dot product or inner product. So we can recall the dot product of two vectors in R3 as just the sum of all three of their entries, where you take the first entries, multiply them, the second entries, multiply them, and the third entries, multiply them. So make it a little bit more clear. They look like U1, U2, U3, dot, V1, V2, V3. The inner product or dot product is me drawing straight lines across, multiplying each of those, and then adding them together. And it's good to know here that, at least according to the author, you've already referred to this as an inner product. You definitely should. So this is where you should be jumping. If anybody ever talks to you about an inner product, your mind should jump to the dot product, but then you want to start getting a little bit more willing to broaden your mind. That's what we'll see in the rest of this section. But the dot product is useful because we can also create magnitudes from it. If we take the square root of a dot product, we gain a magnitude, or we gain a norm, or however you want to think about it. This is the length of a vector. In some sense, the distance of an element of the space away from zero is one way of thinking about it. That's what I'll say. Distance of U away from the zero vector. So it's the distance between the two of them. It's given exactly by this norm, which is recovered from a dot product, square root of a dot product. Well, there was also this idea of a Hermitian inner product on complex vectors. And I'm not entirely sure if you did cover that, but according to the book, you did. If you didn't, it's defined as the following. So suppose I have two complex vectors, a1, a2, dot, 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 an, dot, b1, b2, dot, 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 bn. So they're n entries long. Suppose that they have complex inputs or complex values to them. Then we compute the dot product by, it's the same dot product as before, but we have to take a complex conjugate on B. So on each of the entries of B, we get like a complex conjugate here, and then we take more of our traditional dot product. The reason for this is that you actually do recover the complex norm if you do something like that, right? You need to multiply a complex number by its own conjugate to recover a norm, and that's why the inner product gets defined this way as well. So that's just something to keep in mind. If we have complex vectors that we're multiplying, you need to take the complex conjugate of the second one. Now, projections are very useful because they let us extract elements by ways of dot products. So a projection, oops, I wanted to pen form. Projection is extracting an element, I should say a subset of a vector by means of a dot product, and I'll say inner product. Right, this is not a projection by itself, that's the coefficient of a projection. if I multiply this by the vector x1, this is the projection onto x1 of A. So that's another reason why inner products are useful, is they give us this subset notation of a vector. And in particular, this next section, infinite dimensions, it's not really a section, next subsection, infinite dimensions, I'm going to send you over to my other collection of YouTube videos to watch a video on that, because it turns out that there's nothing special about vectors or even inner products in finite dimensions. We can actually extend the whole notion of inner products into infinite dimensions. So I'll send you over to my other videos to watch that. Anyway, that's all I have for today. I will see you in class once you watch my other video. Bye.